Back. In this lesson, we are going to work out one more question on applications of Kirchhoff's rules. This is slightly more difficult, but still I hope you will enjoy this class. Let's look at this question here. Now here we have the question. Here we have together 5 resistors connected in rather complicated circuits. This kind of circuits are usually called wheatstone bridge circuits. You can see the 5 resistors, of which 4 of them are connected along the sides of a rectangle, and there's a diagonal resistor. And we have a potential difference of V applied between P and Q, and the current drawn into the circuit is taken as I, and there are different currents in the circuit and different branches. You can see that here we have I1 through 1 ohm, here we have I2 to 3 ohm, and through the diagonal resistor we have 5 ohm. This is the situation we are in. And then if you apply the Kirchhoff's first rule, you will be able to work out the current in this branch as I1 minus I3. You can see that here. And on this branch through the 4 ohm resistor, the current would be I2 plus I3. That is pretty simple. Now let us see how we are going to work this out. Now you must remember here we have 3 unknown quantities, I1, I2 and I3, and you may be able to get 3 different equations taking into account the 3 loops. There are two triangular loops, one the upper triangle, and then you have a lower triangle here, and then you have a square loop in here. So you are able to get 3 equations, but unfortunately those equations will not be independent equations. So we will get only 2 independent equations in here. So what does it mean? It means that we have to solve 3 unknown variables, but we have only 2 independent equations. It means that you will not be able to solve these equations to get unique values for I1, I2 and I3. That's a problem. So what we will do in this case is that we assign a value for I3, and then we will be able to express I1 and I2 in terms of that particular value. Then you will be able to calculate I also in that value, and we can calculate V, and if you divide V by I, you will get the effective resistance of the combination. So I hope you understand this. We need to calculate I1 and I2 in terms of I3. We need to calculate I in terms of I3. We need to calculate V in terms of I3. Then divide V by I, and you will get the effective resistance of the combination. This is the idea. Now let us look at this loop. First we will take the loop A, C, B, A. Let us look at the loop A, C, B, and back to A. So here from A to C, we are measuring the potential difference opposite to the direction of the current. So that will be 1 I1, that is positive. Then from C to B, we measure the potential difference in the direction of the current. So that will be negative. So 3 I2 will be negative. So you will get minus 3 I2. And from B to A, again we are taking the potential difference opposite direction of the current, so it will be positive. So 5 I3 will be positive, and then that would be 0. So you get I1 minus 3 I2 plus 5 I3 is equal to 0. That is equation number 1. Now let us look at the second loop, A, D, B, A. Where is A, D, B, A? A, D, B, A, the triangular loop at the lower end. This is one, A, D, B, A. Now we start from A to D. We measure the potential in the direction of the current, so that will be negative. So 2 times I1 minus I3, you have to put a negative sign, so minus 2 times I1 minus I3. And from D to B, we take the measurement of the potential difference, it's opposite direction of the current, so that will be positive. So you get plus 4 times I2 plus I3, so plus 4 times I2 plus I3. And then from B to A, again we take the measurement opposite direction of the current, so that will be positive. So 5 times I3 would be positive, so you get plus 5 times I3. Now you simplify all these things, that you can do it on your own. Minus 2in, that is minus 2I1, there's minus 2I3, that becomes plus, so plus 2I3 plus 4I3, that is 6I3 plus 5I3, that is 6 plus 5, 11I3, that is positive. Then I2, 4 times I2, so that is 4 times I2 in here. So the equation you get, minus 2I1 plus 4I2 plus 11I3 is equal to 0. That is equation number 2. Okay, let's see the next one. Now we are going to find out the loop A, C, B, D, A. Where is that thing? A, C, B, D, and back to A. That's a square loop. You actually don't need to do this, because we know that, we wouldn't be, though we get 3 equations, they are not going to be independent. So you will not be able to solve these to get unique values for I1, I2, and I3. So you have to assign a specific value for one of the currents, and then you may be able to express the other 2 currents in terms of that particular assigned value. But in any case, just for the fun of it, let us do this. So it starts from A. So A to C. A to C is opposite direction of the current, so it will be 1I1, that is plus. From C to B. C to B, it will be in the direction of the current, so this is minus 3I2 in here. Then from B to D, it's in the direction of the current, so that will be negative. So minus 4 times I2 plus I3, minus 4 times I2 plus I3 in here. Then from D to A, it's opposite direction of the current, so it will be plus, so plus, that is positive 2 times I1 minus I3, positive 2 times I1 minus I3 is equal to 0. You simplify this, you can do it on your own. There's nothing in here. For example, I1 is here. 1 I1 you can get from here, 2 I1 you can get from here, together it gives you 3 I1. Minus 3 I2 is here, minus 4 I2 is here, so that will give minus 7 I2, and then minus 4 I3 is here, plus 2 I3 is here. So now minus 4 I3, and this is also minus 2 I3, that gives you minus 6 I3, that is equal to 0. That is equation number 3. So you got all the 3 equations in here. Now I1, I2, and I3 do not have unique values, because these currents depend on the voltage applied across the circuit. Because the equations may not be independent, you will not get independent values, unique values for I1, I2, and I3. And in practical, the reason is that the I1, I2, I3 values depend on the applied potential difference. If you change this to other values, for example, you can take V is equal to 5, V is equal to 8, V is equal to 12, V is equal to 15. In each of all these cases, you will get different values for I1, I2, and I3. So you cannot have independent values, unique values for I1, I2, and I3. Because these currents depend on the voltage applied across the circuit. Therefore, assign a specific value for any of the current. Say I3 is equal to X. So we are going to assign I3 is equal to X. Now we are going to work out I2 and I1 values in terms of X. That's the plan. Let's do that. Then we solve any 2 equations to get the other currents in terms of X. So we rewrite the equation 1 and 2 as follows. So 1 and 2 equation, we will replace I3 with X. So so this is the first equation. If you replace it with I3 with X, you will get the equation I1 minus 3I2 is equal to minus 5X. That is equation number 4. Then 2I1 minus 4I2 is equal to 11X. That is equation number 5. So this is actually equation number 1 is itself, and this is equation number 2. Only thing, we replaced I3 with x. Keep that in your mind, because I have made a mistake in here. Instead of typing in 4 here, I have typed in 1, and instead of typing in 5 here, I have typed in 2. So, but basically the idea is the same. So don't make anything, don't get confused on that. So what we are going to do to eliminate, we plan to eliminate I1 here. So you multiply this equation by 2 and then subtract this equation from that. So this, if you multiply this with 2, you will get 2I1 minus 6I2 is equals to minus 10x. So you subtract this equation 5, not equation 2, which is exactly equation 2 with I3 replaced with x. So anyway, we are going to subtract this equation from 2 times this equation. So 2I1 minus 2I1, the I1 just vanishes, and minus 6I2 minus 4I2 becomes minus 6I2 plus 4I2, that becomes minus 2I2 minus 5x. Then here you get minus 11x, no, minus 10x, because you have to multiply it with 2. So minus 10x minus 11x, it becomes minus 21x. So you get minus 2I2 is equals to minus 21x, and minus get cancelled. And you take 2 to the other side, you will get I2 is equals to 10.5x positive. I2 value is positive 10.5x. Now you can substitute this value of I2 into any of these equations, and you may be able to get I1 value. So you can write I1 is equal to, you take 3I2 to the other side, it becomes plus 3I2. So plus 3I2 minus 5ix, and 5x. So remember that I1 would be plus 3I2 minus 5x. So plus 3I2 minus 5x. 3 times 10.5. That is 31.5 minus 5x. So 31.5x minus 5x, that will give you 26.5x. So I1 value is 26.5x. I2 value is 10.5x. Now you can calculate the I value, because I value will be I1 plus I2. So take a look at here. Here we have the solution I1, I2 and I3. I1 is equals to 26.5x, I2 is 10.5x, and I3 has been assigned x. The total current will be I is equals to I1 plus I2. If you add them together, you will get 37x. Now we need to work out the potential drop across DAC in terms of x. So we'll see how we are doing it, because the diagram is not in here. You might get confused. So let us take a look at the diagram. You can see in here. So we need to find out DAC potential. This is what we are going to do. Now take a look back. So DAC, you can see in this current you will get 2 times I1 minus I2. Here in this across the resistor, 1 I1. Let us see what's the equation. 2 times I1 minus I3 plus I1 is equals to 2 times 26.5x minus x plus 26.5x. If you work it out, you will get V is equal to 77.5x. That's what we have got, 77.5x. So I value we got 37x. V value we got 77.5x. So we can find out the effective resistance R effective by dividing V with I, that is 77.5x divided by 37x. When you divide it, you will get the effective resistance of the combination as 2.09 ohm. That was an interesting question. Hope you have enjoyed that class. Thank you. Thank you very much.